All right, here's topic 5. We're going to start with 5.1, where we're going to look at the relationships in triangles. Triangles are going to be a big part of this class from here on out until we get to topic 10 with circles. There's no avoiding them in geometry, and this is really elementary trigonometry at this point. And it's just saying, right now we're just going to think about this. What is the relationship between a segment and the points on its perpendicular bisector, between an angle and the points on its bisector? So how can you find the points that are equidistant from the endpoints of A, B? And what do you notice about these points and their relationship with A, B? Before we answer that, normally in class I would do, some stuff to lead you down the path. Well, let's look at this first. You guys can pause this and copy it down. I'm just going to keep talking. So our perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. All that's saying is if my line L here cuts line segment XY in half, then it's the same distance to go from X to the line L as it is to go from Y to the line L. And just kind of annotating on the screen really quick, what that's saying to us is this. If however many units this is the same number of units. Now, we can see that very easily because we know what these marks mean now. These congruency marks mean they're the same length. So our perpendicular bisector theorem just says if a line L, is the perpendicular bisector of XY, then we get XQ and QY are the same. It's also telling us, though, something nice here, that PX is equal to, or congruent to, PY. And now we have our converse, right? Remember, our original conditional statement here is if P, that goes from here all the way to here, then Q is everything after the word Q. And if we go to our next slide, we're going to see that we went from P implies Q to Q implies P. And what that means is when we look at this next slide, we're going to see that it is equidistant from the endpoint of the segment, and we're talking about a point. So let's see it. If a point is equidistant from the endpoints of a segment, right, it is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So now think about how nice this would have been to know in the topic 3 and 4 test. And that's simply saying if line L cuts through from P to Q, and these are equal, right? Then it is on the perpendicular bisector. So we can also say now that this and this is true. So this is an isosceles triangle. Keep that in mind. This converse of the perpendicular bisector, the way it's presented to you is always going to work with just an isosceles triangle. And they're just saying, if we have this any isosceles triangle, and we draw a perpendicular bisector such that it hits or cuts right through the top point, so it bisects this, and it bisects the opposite side, and we're going to have a perpendicular bisector. So we're going to do a quick proof, not really a formal proof. We're not doing a 2-column. We're not doing a paragraph proof. We're just going to prove the perpendicular bisector theorem. If you want to see formal proofs, I just uploaded onto EDSB, Google Classroom, and the Classroom website examples of proofs in our writing assignment that's going to be due on December 13th. So as I sit here recording that, it's 1 month and 2 days away. And what we're given, let's do this proof really quick. We're given that line L is the perpendicular bisector of X, Y. So here's line L, and it cuts XY into half because it's a bisector. And now we need to be able to prove that px is equal to py. But to do that, we need to fill in the rest of our given information. If it's a perpendicular bisector of xy, we can add these congruency marks down here. And we can add these here, but we don't know why, right? That's what we're trying to aim to prove. So what we can do, though, is our old buddy side angle side. And that is simply this. I draw this line through here. Well, isn't PQ always going to be congruent to PQ by the reflexive property? So there's our first side. We know from topic 1 that all right angles are congruent. So that's our angle. And then by definition of a perpendicular bisector, it cuts x, y in equal halves. So we can say those are congruent. And that is our side. And as you can see, it just kind of fell into place for us. We've shown that these two triangles are congruent by side angle side. And remember, corresponding parts of congruent triangles are congruent, which means once I show this criterion is true, which I just did, then all corresponding parts of the triangles are congruent. So if you think about it, we have two right triangles here. This would be PQ, PQ, and this kind of helps you see that the reflexive property is true as well, right? Obviously PQ is equal to PQ on both of these triangles. And we were able to do this. Well, we have, here's our side angle side setup. And since I can easily see now that this one would just have to reflect across this line to be the corresponding congruent parts lined up, I can now say that all the parts that are corresponding are congruent, and therefore these are the exact same triangle. So it might be a little confusing, but I think having topic 3 and 4 under our belts gives us a lot of tools here to cover this up, or not cover it up, but to do it. The first one being that, I can't scroll back yet, there we go. If I think about this right here, this line cutting it down could easily be my line of reflection, and I can see that x would come over to y, and they would map onto each other. And that means that q, so PQY and PQX would be the same angle when they map over. They're the corresponding congruent parts. This, by definition, XQ and QY of a perpendicular bisector means this and this are congruent. And now I have side angle side congruency, so I can say all parts of these triangles are congruent if they're corresponding. So what does that do for us, though? Let's look at what we're really going to be working with here. This is a little algebra mixed in. What I can do here is a couple things. I have triangle ABD, right? From A to B, B to D, and D back to A. And then I have this line right here. And I have to ask myself, is AC the perpendicular bisector? No, that's not trying to cram it there. Is AC the perpendicular bisector of BD? Well, just by examination here, and we're not trusting our eyes, we're using the given information. I have a 90-degree angle, which means perpendicular, and I have BC is 11, and I have CD is 11. And since 11 is equal to 11, I can then say that the magnitude or length of BC is congruent to the length of CD. So if we go back on your notes that you just took, the two things that help you, or the two requirements for congruency or a perpendicular bisector here, is that the line that runs from one vertex to the opposite side meets that opposite side at 90 degrees. It's done that. It was given to us. And it cuts the opposite side into two equal halves. Well, since 11 is equal to 11, I can say we definitely have a perpendicular bisector here. Now, from that, I'm going to change colors because this is all just my thought process right now. We're not actually solving anything yet. Just like I showed you on the last slide, by the reflexive property, let's just do that quick proof. Let's not even call it a quick proof. Let's call it a lazy proof. First, AC is congruent to AC by the reflexive property. Then my second one is here, ACB let's make that angle ACB. Let's just start over. That's just all around bad. Angle ACB is congruent to angle ACD because right angles are congruent. And then BC is congruent to CD, and that's just given because it was already on there. We didn't have to do anything. So here I have a side, here I have an angle, here I have a side. So now that I have side angle side congruency criterion satisfied, I know that both these triangles are exactly the same. So I know that all of the corresponding parts of these congruent triangles are congruent. That's just simply CP since side angle side is true, and CPCTC, or the corresponding parts of congruent triangles, is a theorem that we know is true. We can say AB is congruent to AD because those are the corresponding parts, right? If I reflect this over that line, AC, B goes to D. AC is still the same line on both triangles. ACD and ACB, because B is over here now, right? And remember, the identity is if we flip it over the line it's on, it just stays in the same place. So now we're showing that these are all congruent. It's really easy to see that 11 lands on 11, 90 degrees lands on 90 degrees, and our reflexive property. So that means, long story short, those two are congruent. And since AB is congruent to AD, we can do some basic algebra 1 and substitute AB for its value of its expression, 6x minus 10. And since we're no longer talking about side lengths, we don't need that similarity piece. It's just equal since we're dealing with numbers. We can come back up here and say 3x plus 2 is equal to 6x minus 10. And we can just solve for x. I'm going to try and keep my x positive. 3x is equal to, let's go ahead and just do all the steps. 2. Add 10 to both sides. 3x is equal to 12. And therefore, x is equal to 4. But that's not asking, that is not our final answer, right? It says what is the value of AD. Now remember, when they say value of a line segment, what they're really asking for is the magnitude or the length of that line segment, right? So now that I know AD is 3x plus 2, and I know that x is 4, I can do that, and I get 12 here. So the length of AD is 14. Now, just to make sure I'm right, or that I've set this up right, but in all honesty that I just solved for x correctly, I'm going to use this one, AB, to check. Since these are labeled congruent because corresponding parts of congruent triangles are congruent, both of these expressions should give me the same answer if I plug in this value of x. So what is 6 times 4 minus 10? Well, we have 24 minus 10. And AB is equal to 14. And just like we said here, AB is congruent to AD, and 14 is equal to 14. So this is one pretty common problem style you're going to have on the test, homework, and midterm. Let's look at the next style. There it is, all typed out nicely for you. I apologize. So here's our 5.3 theorem. Go ahead and pause it, copy it. As soon as you hit play, I'll be talking about it. The angle bisector theorem says if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. That's a big one, right? If a point is on the bisector. So let me start highlighting some of this stuff just so we can see. So we can see that this is in fact the bisector, right? Right. So the line AD is what's cutting BAC in half. Let me write that just so we can follow. Line segment AD, well, that's a B, buddy, bisects, that can't convince you that's an S. So AD bisects angle BAC. That's given, right? If a point on the bisector is on the bisector of an angle. So the bisector, this is the bisector. And what's kind of cool about this, right now, maybe a little confusing, but for the rest of the year, it's going to give away a lot of the answers right away. If we can show that a point lies on this line AD, and is always the same distance from here to here as it is from here to here, as long as this is at 90 degrees. Now, horrible drawing, I know, but I'm just giving you that little preview. We're going to talk about it more in just a second. Let's finish breaking this down before we go on. Then it is equidistant from the two sides of the angle. I'm going to switch colors. Let's go green, drawing tool. So what it's saying is if this happens, then BD is equal to CD. And that's pretty cool because now, if I were to not have those marks there, and I gave you something like this is equal to 3, then you can look at this and say, well, AD bisects BAC, and it hits this at a right angle. So then that means from B to D is the exact same distance as it is from D to C, as long as DC also hits it at a right angle. And since that's true, we have that statement to make. Now let's actually try it out on a problem instead of just doing in the abstract. It'll make it a little bit more concrete once we work on one in just a second. This is the converse, and all that's saying now is, let me put this here. So what we were able to say from this one is that these two are equal. The converse is going to say the other thing. If we already know these two are equal, if that's our given, then we can make that statement. So let's look at the converse. We'll pause it, and then we're going to jump right into the problem set. So then now what we can say from this one is simply that these two are congruent. So let's look at a problem that we're going to be solving on the homework test and midterm going forward. I'm given this here. I have KJM. I'm not going to call that a triangle because it's not straight here. But I do have two triangles, right? I have triangle KJL and I have triangle LJM. I can also see that KJM angle KJM is bisected. That's an extra E. It is bisected by JL. Which then tells me that anything that comes from my bisector, my JL, leaves there and hits the outside of my angle KJM, as long as it hits at 90 degrees and they start at the same point, these two side lengths here are equal. So now I can say that KL is, yes, we're going to call it congruent to LM by, and let me make sure I pick the right one. So this time we know the angles are bisected, so that's going to be theorem 5.3, the angle bisector theorem. So let me write that. And to solve for those, since I know KL and LM are congruent, I can just say 2x plus 3, that's my KL, is equal to, remember, no similarity mark needed, even though we haven't covered similarity, but we did talk about why those two are combined, is equal to LM, that's 4x minus 11. Again, I'm going to try and keep my x positive. This is just going to give me 14 is equal to 2x. So x is equal to 7. Now, obviously, once again, it wants the value of KL, which is just another way to ask for the length or magnitude of KL. And I know that KL expression is 2x plus 3. And I know that x is 7. So what I'm going to have here is 17. How do we check it? Well, if you said check LM for its actual length by substituting in our x, then you're absolutely right. It's going to give me 4 times 7 minus 11, which is also 17. Since 17 is equal to 17, this also holds true. So we can say without a shadow of a doubt that the length of KL is in fact 17. All right. Pause here if you want to see it typed up nicely. Here is kind of our summary that we always do. We have theorem 5.1, the perpendicular bisector theorem. Let's just kind of speed run these really quick. If I have a line that cuts through a triangle that hits the opposite side at 90 degrees and cuts the opposite sides in half, then it's an angle bisector. That line PM is an angle bisector. If I have a line that cuts this in half, then I can see right here, because it's cutting this guy in half, I'm going to have side, angle, and then by the reflexive property here, side, which would then force both of these triangles to be congruent, which means that here and here, oh, why did I double that up when it's already doubled up? Those are also congruent. So the perpendicular bisector is a nice little tool to have in our toolbox here. The converse of that, again, I just showed you both, right? My original if was the perpendicular bisector theorem. And then when I just did this, then I was really just covering this because it's what it tells us. The angle bisector theorem tells me that if I have a large angle like ABC, and I have an angle that cuts right through the middle of that, right? Because that's what they're showing me here by showing that it's bisecting. Any point on this line, I can pick a point right here. As long as it hits this line, like if I draw the line segment between them, let's call this R. As long as R to BC or R to BA hits at 90 degrees, then my line segments here are equal to each other. Of course, mine's a little jumbled, but theirs tells you, just like you guys know, the angle determines the length of its opposite side. And since these angles are the same and these are congruent triangles, then these opposite sides are congruent. And here it's telling us exactly that again. If I have angle ABC and BP is the bisector of AP, or when it cuts through, it makes AP and PC the same. You can also see that if I flip this and I treat BP as the line of reflection, then I have two very congruent triangles. So then, since these angles are these side lengths are the same, the angles that made them must also be the same. So what I want you guys to do, and try not to pause the video so you can just copy the answers, but I'd like to hear from you, and I want you to tell me just kind of what is the relationship between a segment and the points on its perpendicular bisector, between an angle and the points on its bisector. That was what our bell work was, and I know I said we'll come back to it. This is what I meant by come back to it. And then I want you to look at this person's work and they said river says that Km, that's the ray Km, is the bisector of LKJ because Lm is equal to Mj. Explain the error in River's reasoning. So for River's error analysis, I know I said try not to pause it, but it's tropical storm time, so we'll leave it up and we'll talk about why it's not working. We do not know, right? Remember I said that this is really important, that Lm is perpendicular. We weren't given this. We also weren't given this, right? Those are those two things we just put up on the review screen. You have to have, to do this, you must know that these are perpendicular, or that, or that the angles are bisected to get that those are equal. It's not enough just to know these two are equal unless we know either this is the bisector of the angle LKJ or KLM is a 90-degree angle as well as KJM. So be careful when you do these. All right. This one I'm going to go over quickly since we did do these a couple times. If JL is 14, so we can start filling that out. I'll do that for you. JL, the whole thing from J to L is 14, and ML is 7. What is JK? Oh, sorry, and KL is 10. So it wants to know what is this. Now, you know that this is a bisector, a perpendicular bisector, because it lands right here, and 14 minus 7 is 7. And since we have that these two sides are equal and this 90 degree, we know that that is a perpendicular bisector. So not too much left to do from here. And for our final question today, I'm not going to move forward on these. You guys solve these, put these in the YouTube comment. If I see your comment on the video, then I know you watched the whole thing, and I will give you some sort of bonus for doing it. Thank you. Stay safe during the hurricane, and I'll see you on Monday or Tuesday of next week, where we'll go over the writing assignment. Please read the writing assignment, the document I put up today. It covers a lot. It also has the special tutoring dates on it. You also notice one of those is during the fall break. And that way you don't have to worry about other classes. We can just sit for the 2 hours and go over that writing assignment together.